Okay, in this lecture, let's discuss section 1.3. Every time. Okay, good. Complex numbers, quadratic equations in complex number systems. Complex numbers, quadratic equation. Quadratic, oops, my bad. Quadratic equations in the complex number system. Okay, let's see. We actually, let's see how do we understand the stuff. So originally we study numbers. We have 1, 2, 3, 4, 5, and so on. We have natural numbers. We have natural numbers, and then we know what is 4 minus 3 and what is 10 minus 2. We can get it. We can do subtraction, but it's not always successful, right? It's not always successful. Sometimes if we have 2 minus 10, then in this system we have no idea how to do it. We have no answer. So in order to solve this problem, we introduce new type of numbers, negative numbers. Okay, we have a negative, and also we have a 0, if you want. This is a natural number, and then we have negative numbers and a 0. 0 is not natural, 0 is an integer. Okay, so after we introduce the negative numbers, we can completely do the subtraction. Addition, we can always do it in the natural numbers. The problem comes from the subtraction. So after we introduce the negative number, we know that 2 minus 10, we just give it a new symbol. We put this minus sign in front of 8, and we call it a negative 8, right? So we expand our number range from natural number to all integers. Okay, so now we are satisfied. We are satisfied with the integers. We can do addition, we can do subtraction without any problem. And then with a lot of practice, we know we have multiplication, like 2 times 4, 8, and we also know that if we have 4, if we have 8, then we need a number 2, so that 2 times 4 is 8. Basically, that's a quotient. Okay, so 8 divided by 4 is equal to 2. Multiplication is not a problem for the integers. You do multiplication over 2 integers, it is still an integer. But when we have division, you see here, it's always either subtraction or division, it will give us problem. When we have division, sometimes when we have 5 over 3, then what is this number? It's not an integer. It's not an integer. It's not an integer, we definitely need this type of number. So we introduce a rational number. We introduce a rational number. We consider it, we create this symbol. Every time when we introduce a new large class of numbers, we always create some symbol. So we write the answer as a 5 over 3. We write the answer of 5 divided by 3 equal to 5 over 3. This is a new, you see, It's different from the integers. This is different from natural numbers, right? So we get a rational number. Okay? And with the rational number, here is addition, subtraction. With a rational number, we can do addition. We know how to do addition. We know how to do subtraction. We know how to do multiplication. Integer is also good with multiplication, but we also know how to do the division. Very good. So you will see that whenever you have a class of numbers, you have some operations. This is good with addition. Well, you have some operations, and from this operation, sometimes it is good, though this class of numbers are compatible with operation. Sometimes it is not good with certain operation. It's not good with certain operation. We are going to expand our class of numbers so that the new class of numbers is good, is compatible with this type of operation. And then we invent other operations. And from other operations, we will see a new problem. With this new problem, we continue the expansion of numbers. We get a division, right? After expanding this class of numbers, we get an even bigger class of numbers. All right? And now we're fine. We have addition, subtraction, multiplication, and division. It is they are compatible with rational numbers. And then in this part, in the rational numbers, we have power, right? We have 2 squared is 4. 3 squared is 9. Power. And when we have power, we can have root. Power is okay, but root is a problem. What is square root of 2? If you want, let's not put it. Which number its square is equal to 2? Which number square is equal to 2? And this number is not in the is not in the set of rational numbers. So we have to expand. Again, expand. This is one way, one reason to have irrational number. There are other reasons. I just want to get the expansion about certain operations. So we will get irrational numbers or root numbers. Not all irrational numbers are from this way. This is just one line to discuss it. So I'm trying to say here, I'm going to create a new symbol. You see, square root of 2. I say its square is equal to 2. This one is not a rational number. It's an irrational number. Okay? So when we try to expand this number system, we always keep creating new symbols. We always keep creating new symbols. And with this one, we can take a root of a square root of all positive numbers. Square root of all positive numbers. So we partially finish the job. Okay? It's partially done because here I still need it to be positive. I get the square root of 2. Now, in order to completely finish this job, to take square root of all numbers, we have to handle this problem. X squared is equal to -1. What is x? This x is not irrational. It is not an irrational number. This x is irrational. Okay, so in order to answer this one, we need to continue the expansion of a number system. We are going to give a new symbol for this equation. That's our starting point of the complex numbers. So the imaginary unit, which we denote by I, is the number. You see here, you have a number. You consider it as a number whose square is -1. Okay, imaginary, you have to really imagine it. That is, I squared is equal to -1. See, we gave a new symbol. Here, this is new symbol compared with the natural numbers. This is new symbol compared with the integers. This is new symbol compared with rational numbers. Here's the new symbol compared with rational plus irrational is a real number. This is compared with real numbers. Real numbers, you can really feel it or touch it. Imagine a number, you can imagine it. Okay? By the way, how do we feel what is the square root of 2? What is the square root of 2? How do we feel this number? What does this mean? It means if you have a square with length 1, this is square with length 1, then this diagonal is square root of 2. You can really have it, okay? And what is a pi? What is a pi? If you have a circle with radius 1/2, the length, the circumference of the circle is pi. Circumference of the circle is pi. So we do have some way to feel those numbers, even if they are irrational. But for the imaginary numbers, they cannot be represented like this. Okay? You can only say, okay, what is the imaginary unit? Its square is -1. What is 1/3? You add 3 1/3, you get 1. That is a condition. So for those numbers, you only feel it by the condition. Okay? So I squared is equal to 1. So this is imaginary unit. Imaginary unit. Okay? So now with the imaginary unit, we can define so-called complex number system. What is a complex number system? You see the second definition. Complex number. Complex numbers are numbers of the form a plus bi, where a and b are real numbers. Okay, so what is a complex number? 2 plus 3i. This is a complex number. Or 3 minus 2i. This is also a complex number. You have a real part, you have another real number times a imaginary unit. The composition, the sum or the difference is a complex number. And in this case, you actually have a equal to 3 and b equal to -2. Be careful, here's always addition. In the complex number, if you want to determine a and b, you must write it as addition, a plus bi, then you can determine what b is. B and a contain the sum. B and a contain the sum. Okay? So this type of number is called complex number. You see here, we have another symbol, another new symbol. Okay, and then the real number a is called the real part. It does not include I, so it's a real part of the complex number. A plus bi. And the real number b is called the imaginary part of a plus bi. I is an imaginary unit. It is a unit. B is imaginary part. Okay? I is imaginary unit. With I square is equal to -1. I square is equal to -1. Okay, so what is a complex number? Whenever you have a number with such form, it's a complex number. And this a plus bi is a standard form. Standard form of the complex number, of a complex number. You will see that later we can represent a complex number in many fancy way, but since there are several phases for the complex number, we want to know what is a standard phase of it. So this is a standard form, right? Yeah. Okay, when we have a complex number, we will see that if b is equal to 0, if b is equal to 0, a plus bi, 0 times whatever number, it doesn't matter you have integers, negative numbers, you have integers, or you have fractions, or you have irrational numbers, or you have complex number. 0 times whatever number is always 0. So a plus 0 times I becomes a. A is a real number, so this implies all real numbers are complex numbers. All real numbers are complex numbers. So this conclusion really tells us we do expand our number system. By this expansion, we still include the old number system. In our mind, we consider real number, and now we consider complex number. A complex number contains the real numbers. Complex number still contain the real number. All the real numbers are also complex numbers, but with the imaginary part equal to 0. Imaginary part is equal to 0 for real numbers. And what happens if the real part is 0? Real part is 0. 0 plus whatever number is just that number. It's a bi. And this type of number is called, it has no real part, a pure imaginary number. Right? This one looks like a mixed one. You have a real part, you have an imaginary part. Here you only have imaginary part and no real part, so it's like a pure imaginary number. All right? It's a pure imaginary. If the imaginary part is 0, so you don't call it a pure real, it's just a real number. Okay? Okay, so now we have a brand new number system. When we have a new number system, we have to study its addition, subtraction, multiplication, division. It's like when we have negative numbers, we have to know what happens if you have a negative number plus a negative number, or negative number plus a positive number, or negative number times a negative number. You have a new system. When you have the rational number, remember we recalled how do we add to rational numbers, how do we subtract to rational numbers, how do we multiply to rational numbers, right? And when we have root numbers, we also see, well, how do we do the product of two root numbers, square root numbers, stuffs. So every time you have a new number system, you should try to practice their addition, subtraction, multiplication, and division. So the first part, we're going to add, subtract, multiply, and divide complex numbers. Of course, if your complex numbers are just the real numbers, you know how to do it. Okay? But if they're really a mixed part, a plus bi, then you have to have the following. Okay, before we do those operations, we have to say, okay, you have this expression of a complex number, you have that expression of a complex number. How do I know they're equal to each other? Okay, so you have two complex numbers. You have two complex numbers. How do I know they are the same thing? One complex number is equal or is the same as the second complex number if and only if they have the same real part and they have the same imaginary part. Okay? Two complex numbers are equal if and only if they have the same real part and they have the same imaginary part. This is about the comparison of two complex numbers. You can compare them, you can let them equal by examining the real and imaginary part. Okay? Second. If we have a complex number, one complex number and second complex number, how do we add two complex numbers? The sum of these two complex numbers is equal to the third complex number with the real part a plus c. You add real part with imaginary part b plus d. You add imaginary parts. A plus c plus parenthesis a plus d times I. Okay, so this is our addition. And subtraction. A plus bi minus parenthesis c plus di. It is, you're going to do subtraction among real part plus subtraction among imaginary part. Okay, remember they are mixed. You have real and imaginary part. You can only handle real part with real part, imaginary part with the imaginary part. You cannot mix them. You cannot mix them for addition and subtraction. Okay? Okay. Good. Now let's see the example. Well, the example will be very straightforward. If we have a 3 plus 5i and plus negative 2 plus 3i. How do we add two complex numbers? We're going to add these two numbers. 3 plus negative 2, 1. We're going to add these two numbers. 5 plus 3, 8. 1 plus 8i. And that's it. as simple as a real numbers, as simple as real numbers. Just add a corresponding part. In other words, it's like to combine like terms. It is like to combine combine like terms, terms. So it's like a real part are like terms, imagined part are like terms. You just combine them separately. Second, let's see a subtraction. 6 plus 4i minus 3 plus 6i. Be careful here. 3 plus 6i, even though it looks like a sum, for us it's one complex number. For one such complex number, you put parentheses. Be careful. I write this way, and it's different. Like, it's different from I write this way. These two things are not equal. This means you really just subtract 3 and you're going to add 6i. These two things are different, are totally different. Okay? Put parentheses if you consider this as one complex number. Here I actually consider it as two complex numbers. I do this once and do this second time. Okay, now let's see. The subtraction means the subtraction for each part. 6 minus 3. 4 minus 6. 4 minus 6 is negative 2. 4 minus 6 is negative 2. Okay? Okay, so that's addition subtraction. Well, they are so straightforward. So we just do two examples and that's it. Okay, so we're okay with subtraction, addition and subtraction. Now let's talk about multiplication. Multiplication. For the multiplication, what do? You have a sum times another sum. For the product, remember, product sum, they have distribution rule. It means I'm going to do the distribution. A times C, A times BD. A times C is it's between real numbers, it's AC. A times DI, A can only be multiplied with D, so it's A times D. This is new imaginary part. I is a unit, like 2 apples. When you multiply, you will multiply by 2. You multiply 2 apples by 3. It's a 2 times 3, not apple times 3, right? So 2 times 3 is 6. So here is the same thing. You only multiply A with D, the numbers, not a unit. Okay, and then you have BI times C. BI times C, same. BC times I. BI times DI. Okay, let's put it here. BI times DI. Okay, so let's study the last term first. I times I, we see it. Remember, what is the property of I? I squared is negative 1. What is square? I times I. Square means I times I. So I times I is negative 1. I times I is negative 1. That's a way to change a complex imaginary unit to the real numbers. That's a relation. You multiply I by itself, you get a real number. So that's why you have to imagine it, what this number is. So I times I is negative 1, so you have to change it to be negative sign. So it's AC plus ADI plus BCI and minus BD. Minus BD. Right? Negative sign comes from I squared. And then we're going to combine like terms. AC minus BD, they are real number. ADI plus BCI, 2 apples plus 3 apples is 5 apples. AD plus BC times I. So this is multiplication. This is a multiplication. So multiplication of 2 complex numbers. come from the distribution of multiplication with addition. Just distribute one by one, and be careful you have I squared. I squared is equal to negative 1. So you have negative BD. So AC minus BD, parenthesis plus another parenthesis, AD plus BC times I. Well, this is the formula, but this also gave us the routine way to do the multiplication. We possibly will not strictly directly memorize this formula. We will just memorize how we do the distribution. Okay, so for example, let's see. 5 plus 3i times 2 plus 7i. How do I do it? I will never try it this way. It's so similar, so close. So I really do the multiplication. 5 times 2, 10. 5 times 7i, 35i. And 3i times 2, 6i. 3i times 7i is 21i squared. This is the first time I do the multiplication. I keep this I squared. I squared is negative 1, so it's 10. 35i plus 6i is 41i. It's minus 21. I squared is negative 1, so it's minus 21. So the answer, 10 minus 21, negative 11 plus 41i. See? This is the answer. You can try the formula. You will have the same answer, but I don't bother to memorize it. I just do the plain computation. It's not difficult. Even though you try the formula, you also do the same, more or less the same computation. All right, so let's see if we have one more. 2 plus I times 1 minus I. Okay, 2 times 1 is 2, 2 times negative I minus 2I, I times 1 plus I here, I times negative I, so it's minus I squared. So it's 2, negative 2I plus I is minus I. Minus I squared is negative 1, minus I squared is plus 1, minus I squared, this is negative 1, minus negative 1, plus 1. So 3 minus I, and that's it. 3 minus I. See it? So don't forget I squared is equal to negative 1. Whenever you have a subtraction with I squared, it becomes plus I. Well, this is a multiplication. The next, we're going to do the division, but division has issue. In order to solve that issue, let's see a technical setting. Actually, it's also very important in geometry. So we have a plus bi. This is a complex number. This is a standard form. Remember, standard form is always a plus bi. You have plus, you can also have minus, right? So if z equal to a plus bi, usually we use letter z to represent a complex number, and this possibly come from German, because in the German the number, that word starts with z, Zahlen. Well, if I'm right. Okay, if z equal to a plus bi is a complex number, then its conjugate, its means the conjugate of z, its conjugate denoted by z bar, use z bar, is defined as z bar is, well, you can write z bar, you can write big bar above a plus bi. It's defined to be a minus bi. Okay, so what is the conjugate? Conjugate just means you change the sign in front of I, in front of bi. You only change the imaginary part. For example, if we have 2 plus 3i, I change the sign in front of the imaginary part, it will be 2 minus 3i. Or if you have negative 6 minus 2i, the conjugate. Remember, the real part, we always copy it. Imaginary part, originally it's negative. You change it, it becomes positive. You just change the sign in front of I part, bi part. Okay, so this is this is exactly the complex conjugate. It's called the conjugate of the original one. It has a pair. Okay. This conjugation is about the relation of a pair of two numbers. And if you just separately study one number, this is A, this is B. If you study this number, this is A, this is B. Okay? So conjugation is a relation, but for separate complex numbers, you need to know what is A, what is B. Okay. Well, let's see what is a property of this conjugation. Why are we interested in this? Let's assume we have z equal example. Let's assume we have z equal to 3 plus 4i. Z is a 3 plus 4i, then z bar is a 3 minus 4i. One is a plus, one is minus. Now let's do the product. Z times z bar. 3 plus 4i, 3 minus 4i. Well, let's try. 3 times 3, 9. 3 times negative 4i minus 12i. 4i times 3 plus 12i. 4i times minus 4i times 4i. Right? This is a minus sign. 4i, 4i. Okay. Minus 12i plus 12i, they're cancelled. And I square, I times I square. Square is negative 1. I square is negative 1. With this negative sign, it's positive 1. Plus 4 times 4 is 16. Right? So it's 25. See, you have a complex number. You multiply this complex number by its complex conjugate, but the result becomes a real number. The result becomes a real number. No complex part. Imaginary part. No imaginary part. Well, this is not a special case. It actually represents a general stuff. And also, what is 25? 25 is 9 plus 16. 9, what is 9? 9 is 3 squared. 9 is 3 squared. 16 is a 4 squared. Okay, so this gave us a evidence about the following theorem. If z is equal to a plus bi, then z times its conjugate is equal to a squared plus b squared. If z is a plus bi, then the z times its conjugate is a squared plus b squared. Well, let's try it. What is a conjugate? Conjugate is a minus bi. Right? Conjugate a minus bi. We actually go through those whole process. We just replace 3 by a, 4 by b. So z times z bar, you will get a plus bi times a minus bi. See? We get a parallel copy. A times a squared. you have 9. A times negative bi minus abi, that's negative 12i. And bi times a is plus abi, positive 12i. And minus bi times bi. You have a minus sign, you have bi again. I give you negative 1. bb give you b squared. Negative 1 cancel with this is positive. This plus minus they cancel. So you will have a squared plus b squared. This is a squared. This is b squared. This gave you the positive sign. See? That's exactly what we computed. But here we just use AB instead of a 3 and a 4. Okay? So this is a very, very, very interesting property about complex numbers. For the complex numbers, if we multiply, for whatever complex number, it doesn't matter it's a real or pure imaginary or just mixed term. For whatever complex number, if we want to get a real number out of it, how do we do it? We just multiply it by its conjugate. We multiply it by its conjugate, then we will have a real number. Right? Okay, so let's stop the video at this moment. We will continue the discussion in the next video. The lecture is not done yet. Okay, so we finish this video for the moment. Thank you.